This is the second lecture in digital image processing, DIP, lecture number 2. In this lecture, we are considering the mathematical characteristic of the two-dimensional, which is image. There are two basic mathematical characterization of interest, deterministic and statistic or stochastic. In deterministic image represent a mathematical image function is defined and point property of image are considered. For a statistical image representation, the image is specified by the average. So suppose that the C is representing spatial energy and distributed on an image source radiant energy at the spatial coordinate x, y, and at time t with wavelength lambda. The physical imaging system also imposes some restriction on the maximum intensity of an image. For example, film saturation and cathode ray tube, photo heating, and etc. So this C is between 0 and A. For mathematical simplicity, we suppose that x is between Lx and minus x and y, so, and the physical image, of course, observed only on a finite interval of time. The intensity response of the standard human observed to an image light function is commonly measured in terms of the instantaneous luminance of the light in field as defined by this y integral. This v is the response of the eye. Relative luminosity efficiency. For an arbitrary red, green, blue ordinate system, the instantaneous stimulus value are R with this integral, G this integral, response to the red, response to green, response to blue, and so on. In two-dimensional system, we map the two-dimensional function f1, f2, fn to a set of the output two-dimensional function g1, g2, gm. So m dimensional to m dimensional. This mapping may be represented by O for m equal 1 to m, and this matrix is showing the transformation for two-dimensional O1 operator 1 to M, which is mapping 1 to N from F to G to M, generally as an output. So generally, the output 1 to 1 mapping is GXY is OFXY. The singularity operator are widely employed in analysis of two-dimensional system, especially a system that involves sample of the continuous function. The two-dimensional Dirac delta function is a singularity operator that possesses the following property: the integral of delta xy two-dimensional between, this is infinitesimal epsilon and is the energy is one, and the second call is shift property of the Dirac delta. This singularity operator, like this, the two-dimensional delta function can be decomposed into product of the one-dimensional. So delta xy is delta x multiplied by delta y. The delta function also can be defined as a limit on a family function. A two-dimensional system is an additive linear system if the system obeys the law of additive or superposition. In the special case one-to-one mapping, the additive superposition property requires that operator A1, F1, or A2, F2, this is linear operation in the input, and it pronounced to the output linear combination, additive superimposition of the output A0 over F1, A2, O over F2. A1 and A2 are two constants. A system input function xi can be represented as the sum of the amplitude of the delta function shifting integral. So fx is f eta and zeta eta, delta x minus zeta and y minus delta. This is the convolution. F is weighted factor of the impulses in the xy plane. If the output of a general linear one-to-one system is defined to be G is O over F, then operator over this integral can be written as this one. And this is the impulse response of the two-dimensional. This is in the figure is shown this, and general linear imperative function. Also, the linear operator can be applied into the integrand of the function. So H is the impulse response, and the mapping of the impulse to the new response, impulse response of two-dimensional system. In optical system, impulse response is often called the point spread function, how a point is spreading on the surface or system. And then we can obtain the next page. H is this additive linear operation, X is an additive two-dimensional. It's called the space invariant. So it is not related to space. For a space invariant, X is this. So it is the convolution between F and the impulse response. And in superposition integral, we can use the convolution two-dimensional, and then symbolically it is convolution of F and two-dimensional impulse response. And another is differential operator. The edge detection in image is commonly accomplished by performing a special differential of the image field followed by a threshold operator to determine point of this deepest amplitude change. And then horizontal, vertical. So we have two. This is the differential with X the direction and differential with Y direction. The second derivative in the horizontal vertical defined as dxx and dyy. The sum of these two is the Laplacian operator. Next. The two-dimensional Fourier transform is defined as this, fx5 in Fourier transform is a exponential minus I is the root minus 1, omega xx, omega yy, and omega x, omega y are a spatial frequency Here, a special frequency. In general, the full transform f omega x omega y is a complex number with the real part and imaginary part. So on an image in magnitude, the phase and angle, we can also say magnitude and angle. This is magnitude and the phase phi. And for input xy can be recovered from the Fourier transform inverse Fourier transform, which is inverse function fxy from the f omega x omega y, or operated from the this. This is the inverse of the Fourier transform. If the image function is spatially separated, such as fxy, fy, then fy is this, where fxy, xy, one-dimensional full transform of x. So we can separate two-dimensional by two one-dimensional integral. Also, Fourier transform is a linear operator. So operator A plus B, F1, F2 is A, F omega, F2 omega. And then a linear scaling of the spatial function result in an inverse scaling. So if we expand stretching an axis in one dimension result in the contraction of the corresponding axis in the other domain plus an amplitude change. So expansion is compression and compression expansion. A, a positional shift in the input plane result in a phase shift output. So operator x minus a, y minus a is this, and alternative frequency shift is this. And for two-dimensional convolution, we have operator f in the frequency domain is multiplication. And the inverse of the theorem is also stated like this. In the partial theorem is the energy of a special Fourier transform and autocorrelation function. The transform of the special autocorrelation function is equal to the measure of the square Fourier transform, and the special Fourier transform of the directional derivative of an image is related to the Fourier transform. Also, Fourier transform of Laplacian is image is equal to this. Image fxy is the input of additive linear system with an impulse response xy, hxy. The output of the function is g, like this with this convolution, taking the Fourier transform on both sides is this. And therefore, the Fourier transform shift theorem, the inner part of the Fourier transform, we can obtain this one, performing this one, so the transformation is this. Then an inverse transform is this. So next, we in the next lecture, we uh, uh, talk about the statistical stochastic characteristics of the image, assume a general family of the property theorem, random variable, and stochastic process. For continuous image, the image function xy is assumed to be member of a continuous three-dimensional function xy and t. The stochastic process fxyt can be described completely knowledge of it input. So it is by the probability of density function for the sample of this. So next we stop here, and in lecture number 3 we continue for the stochastic image processing. Thank you very much.